Hello, everybody. This video is about general relativity, the summation of Einstein's work in relativity, where we're going to get deep weird. Whenever I say deep weird, I'm talking about we're going to talk about some very fundamental ideas about how our reality, how our universe operates and is structured, is governed by general relativity. And it's weird because this is not intuitive. It's rather amazing that Einstein was able to come up with these ideas and how wildly successful they have been over the past 100 years, surviving a battery of observational tests and alternative explanations. Every time new evidence becomes available, it ends up supporting general relativity. It has predictions that are still being fulfilled today, 100 years after the entire ideas were put forward. So, one of science's most successful ideas of all time, and it's very, very profound in what it means about the universe that we live in. So, let's strap in, be ready, and let's explore Einstein's general relativity. All right, so Einstein was obsessed with understanding what gravity is. Something about the whole Newtonian sense of things wasn't really meshing well with how he was viewing things and the thought experience he was doing about the universe as he's exploring things and coming up with space-time from special relativity. This idea of gravity is still hanging out there. And a lot of the physicists of the day were having a lot of trouble coming to terms with the modern physics that was developing, some of the new ideas that were developing uh, with Newtonian ideas of gravity. So Einstein really wanted to solve this problem. And in doing so, he's going to shatter our entire idea of what gravity is. In fact, we're going to end this by realizing that gravity is not really a force. It's a pseudo force. It's something that we observe, but is really something else. So it's a force that is apparent. And yes, the way that it manifests itself very much follows Newton's universal law of gravity. But what's causing it is not some force, but rather a warping of space time. And then things just moving around in space-time itself. So this is going to shake our entire conception of reality and bring us to our modern ideas of how the universe is structured. This is general relativity, published in 1915, more formally called the general theory of relativity. And the principal thing that you need to keep in mind with general relativity is that it all rests on this thing called the equivalence principle, which I'll just give, there are many ways of saying this. I'll give you my version of stating it. There is no way to tell the difference between an accelerating reference frame and gravity. They are one and the same thing. Those two ideas are equivalent. Gravity is just acceleration, acceleration is just gravity. Although, really, we're dealing with something bigger than that itself. But you can't tell the difference between acceleration, an accelerating reference frame, and gravity. So what we'd call a non-inertial reference frame and gravity are identical. They are equivalent. And there is no single experiment that can ever be performed that can differentiate an accelerating reference frame from the effect of gravity. And that's where Einstein really, really hammered this idea in, is he came up with a rationale that these two things are the same. And we'll go through the famous thought experiment that shows that, but then was also able to show that there's not an experiment that could possibly exist that differentiates these two ideas. There's nothing that you could do to differentiate an accelerating reference frame from the effect of gravity. And since logic tells us that they should be the same thing, and there's nothing that out there that could tell us that they are different, then they are the same. That's the heart of the equivalence principle. And really, we can see this with Einstein's most famous thought experiment, the so-called elevator thought experiment, where essentially you want to imagine yourself, or in the case of my slides, we have Cartoon Galileo. Welcome back, Cartoon Galileo. It's been a while. But you want to imagine yourself in an elevator in outer space. I never really liked the idea of an elevator because I think just a box without any windows, but I mean, that's kind of what an elevator is, but it's attached to some cables. But essentially, our Galileo right here, our cartoon Galileo, is here in this box, a windowless box, and his task is to figure out what's going on outside the box. Where is he? What are the conditions that he's under when he can't see outside of this box? What we're going to do is we're going to go through two different cases. One where where he's feeling an acceleration, and another case where he's in free fall, a so-called inertial frame, not feeling any accelerations. And then we're going to take a look and see what's going on. So let's just go ahead and dive in. And hopefully as we go through this, you'll see the strangeness and the profoundness of this thought experiment. So case one, we have Galileo here in the box. And we're first going to consider he feels his feet getting pulled down to the floor. He can stand up and he's stuck. He can jump up and down, things like that. Very much like what you're feeling right now. But he asks a question. Is he in a box on Earth? That would explain everything that he's feeling inside his box. He feels Earth's gravitational acceleration pulling him down at 9.8 meters per second squared, the gravitational acceleration of Earth. So Galileo could conclude, I must be on Earth to feel this acceleration of 9.8 meters per second squared. But then he scratches his head and he goes, well, what if I wasn't on Earth and instead I'm just in this box in outer space, and this box in outer space is accelerating. In this case, I've drawn it so it's accelerating upward with an acceleration of 9.8 meters per second squared. Then as this box is accelerating upward, it's going to push against Galileo's feet and he would be sucked to the floor and be feeling that acceleration of 9.8 meters per second squared. So in this case, the acceleration of the box through space is making him feel an acceleration of 9.8 meters per second squared. And as long as that box is accelerating at 9.8 meters per second squared, that would be equivalent. What could Galileo, or cartoon Galileo, do in our box that could tell whether he's on Earth or if he's in outer space in a box that just happens to be accelerating 9.8 meters per second squared? There's nothing, no experiment that exists that could tell him what scenario he's in. If he's in the box on Earth and feeling Earth's gravity pulling him down, or if he's in a box just in outer space and that box is accelerating in one direction at 9.8 meters per second squared. He can't tell the difference. There's no experiment that can tell the difference between those two things. So Einstein concludes those two scenarios must be the same. That this acceleration scenario, where he's feeling the acceleration of the box moving through outer space, changing its motion through outer space, is the exact same as the scenario of him in a box on Earth, and Earth's gravitational field pulling him down at 9.8 meters per second squared. Okay. Kind of a hard pill to swallow, but it does make sense. And it is true that these two are the same thing. Acceleration of a reference frame is indistinguishable from gravity. Therefore, gravity and an accelerating reference frame are the same fundamental thing. All right, so now let's go to another case. What if you are feeling any effects of acceleration or gravity because they're the same thing? So in this case, our cartoon Galileo finds himself again in the box, wondering, who put me in here? This is kind of weird. I don't want to be stuck in a box. But nevertheless, he's in this box and he's trying to figure out what's happening outside around him. This time, he's not feeling any acceleration. It feels like he's just floating in the box. He's in what we would call a free fall. So now he has to figure out what's going on. And one thing, he's like, all right, maybe somebody just dropped me in this box out of an airplane and I'm falling towards the Earth, and the box is falling at 9.8 meters per second with an acceleration of 9.8 meters per second squared, and I'm falling with a acceleration of 9.8 meters per second squared in Earth's gravity. So I'm falling at the exact same way that the box is falling. So it feels like I'm just floating here in space. I'm in free fall. And this is how, say, if you've ever heard of the vomit comet, a plane that flies these parabolic orbits and will simulate 0G, it actually will dive down with an acceleration of 9.8 meters per second squared, and you will go into free fall. So Here, Galileo feels like he's in free fall. Now, if he was on Earth and we gave this enough time, eventually he would go splat. But let's not splat our cartoon Galileo. He's kind of my friend. But Galileo's like, okay, maybe my friends aren't jerks and they didn't put me in a box and shove me out of an airplane. Maybe I just end up in this box and I'm just out in outer space and I'm just floating around in outer space. No net forces, I'm just floating in space. Although we know from special relativity there is no special reference frame, so he would have to be moving. So we better consider the real case where, okay, he's in a box in outer space that's moving through space but not accelerating, a non-inertial frame, as we'd call it. In which case, he's moving at the same velocity that the box is moving, so he just feels like he's in free fall. Can he tell the difference between this scenario and the one where he was falling on Earth in a box? No experiment can distinguish a difference. He is falling. Oh, sorry, I forgot to change the text on that one. And then we finally have another scenario to consider. And this one feels different. And this is where it gets kind of interesting because it feels different, but it's not. So now our cartoon Galileo is in a box, but now that box and Galileo are in orbit around the Earth, just like the people on the International Space Station are. They're in orbit around the Earth. Since everything's moving the same, so the box is accelerating, it's changing its direction in space due to the gravity of Earth. But the motion is the same, so everything's co-moving together. And therefore, this Galileo in a box couldn't tell if he's orbiting the Earth, falling towards the Earth, about to go splat, or just floating through space, not changing, not orbiting anything. So Einstein, with his ideas of relativity and his equivalence principle, determines that in all of these cases of free fall, these all must be the same thing. So free fall, which could be falling freely downward in a gravitational field, is identical to a free fall where you're just moving in outer space at a constant velocity or orbiting a planet. All of those must be the same thing. So let's go ahead and step back and summarize what we just saw. So we had our first case where we have an elevator in Earth's gravity, and the person feels the acceleration of Earth. So they're just basically standing on the surface of the Earth. That could have been that case, or it could have been that the box is in outer space accelerating upward with an acceleration of 9.8 meters per second squared. These two are the same thing. With no other information, the cartoon Galileo, in case both of these cases right here, can't tell if he's in if Earth's gravity is causing the effect or if it's just the acceleration of his box in outer space. No experiment can differentiate. Therefore, these two things, gravity and accelerating reference frames, are literally identical to one another. They are the same. One might say that these two scenarios are equivalent. And this is going to be a core thing of understanding general relativity. It would be a principle of equivalence, an equivalence principle. And then we had this case right here where we had the free fall case. So in orbit and then falling around, Galileo doesn't know if he's in a gravitational field and co-moving as he falls with his box, or if he's just free floating in space. They're feeling net zero forces, so feels in free fall, feels 0g. So Einstein reasoned that this free fall scenario and any inertial state, a non-accelerating reference frame, must be identical. That's the famous thought experiment that Einstein went through to really build the bedrock of general relativity. So let's just go ahead and start looking at some of the consequences. And then I'm going to give you some observational evidence and additional consequences in the next video. just to have kind of 2 short videos to let you digest some of this material. But what we have just sort of seen is that gravity and acceleration are indistinguishable from one another. Why? Because of the equivalence principle. And an inertial frame and free fall in a gravitational field are also indistinguishable. And really, Einstein's genius is going through the thought experiment to realize that these must be the same thing, which quickly leads to the conclusion that gravity is not really an attractive force caused by mass. Rather, what we're really seeing is just things moving in a curved spacetime, a warped fabric of spacetime itself. So the equivalence principle will lead to, so if you can't tell the difference between acceleration and gravity, then, and you can't tell the difference between an inertial frame and free fall in a gravitational field, then really gravity isn't a thing. Gravity is not a force, but a consequence of space-time. The difference is that mass doesn't create gravity. That was sort of the Newtonian idea. Mass warps space-time itself. It bends space-time, and then things just move following the curvature of space-time itself. Mind blown. That's weird. That's strange. That is hard to wrap your brain around because it just doesn't feel like the right answer. But that's because we live here on Earth in a gravitational field. So, the net conclusion, space-time is a thing, thank you special relativity, and it is curved. The curvature of space-time, what is causing the curvature? What is warping space-time itself? Mass is doing the warping of space-time. What we perceive as gravity is not a force, but a pseudo-force, something that appears to exist. And it only appears to exist. It arises from the curvature of space-time itself. And we'll go more into this in the next video. Just want to prime your brain right here. But this is stranger still. Let's leverage one of Einstein's other ideas, that Einstein has mass energy equivalence, that E equals mc squared. So energy and mass are also equivalent. And we just saw that mass is warping space-time. Mass is creating our effect of gravity. But if mass and energy are also equivalent, then energy also itself bends space-time. So it's mass and energy that do the warping of space-time. And then there's sort of the summary that everybody comes to, that matter and energy tells space-time how to bend. It gives us the curvature, the warped space-time itself. So matter and energy do the warping of the space-time. They bend space-time. And then space-time tells that very matter and energy how it's going to move through space-time. So this sort of cyclical. So matter and energy tell space-time how to bend, and space-time tells matter and energy how to move. And really, this unlocks and started to figure out the true way that things are moving. And you may be thinking that all of this is a bunch of BS, but it's not, and I'm going to try to prove that to you in the next video. I do want to go ahead and show you how this kind of works, just so you can start building a model in your brain to try to make sense of this. And the way that we usually think about this is picture, say, a trampoline, and in the middle of the trampoline, you put a bowling ball. And that bowling ball would bend the fabric of the trampoline, making this pool, so you'd have a curvature of your trampoline surface, where you have this big divot where the bowling ball is. That's what this is sort of showing right here. Now think, instead of a 2-dimensional trampoline surface, you're thinking about 3 plus 1-dimensional space-time. Just think about the 3 spatial dimensions, but we can kind of reduce it to 2, so we have a picture in our brain, and we can see the sun is bending space-time. Now, if you have that trampoline model in your brain still, imagine I go out onto that trampoline and I take a marble and I roll it around or within the sort of funnel that the bowling ball is creating, that curved surface. If it was a frictionless surface, so this thing never lost the velocity, I could roll it and it would just spin around in a circle, never falling down to the bottom. It just spin around and around and around. Our closest approximation to that is if you've ever gone into a department store and they have one of the big coin funnels and you put a coin in there and you see the coin spin around and around and around. It ends up going down because of frictional losses changing the velocity, so it gets sucked downward. But if it was a frictionless surface, it would just spin around and around and around. It would be orbiting. And that's how we can explain orbits with this curved space-time. The Earth here is just, it's trying to do its thing. It's just going forward and not doing, well, just being lazy, essentially. It's not going to change its motion unless it's forced to. It just so happens that the surface that it's riding on is not flat like a table. It's curved due to the sun's mass. So the Earth is just being lazy and following that curvature of space-time, just spinning around and around and around. And that's why it's in orbit. It's not gravity that is like giving a force that's yanking on it. It's just following the curvature of space-time. All right, so that's what I have to prime for our next video where I talk about some of the consequences and give you some evidence that this really is the case. I hope you enjoyed this. I hope you enjoyed the thought experiment. I really enjoyed putting together those slides. I will see you in the next video.